Please check out the description below for a list of topics I will discuss in this module. Welcome to our sixth and an extremely high-yield module for USMLE Biostatistics, where we will go over the principles of testing and screening. The goal of a diagnostic test is to identify individuals with or without the disease. New diagnostic tests are often compared to the gold standard, that is the best available test. First, let us review the 2x2 table for a diagnostic test. Again, disease positive and negative are represented in the columns, while test positive and negative are represented in the rows. Each cell of the 2x2 table represents how accurately the diagnostic test is capturing the patient's disease status. If the patient with the disease tests positive with the diagnostic test, that is considered a true positive. Similarly, if the patient without the disease and tests negative for the diagnostic test, that is considered a true negative. Conversely, patients without the disease testing positive for the disease is considered a false positive, while patients with the disease testing negative for the disease is considered a false negative. The sensitivity refers to the true positive rate of a diagnostic test, that is the proportion of individuals with the disease who test positive for the disease. And thus, it is calculated by taking the true positive and dividing it by the total number of individuals with the disease, that is a true positive plus the false negative. The specificity refers to the true negative rate of the diagnostic test, that is the proportion of individuals without the disease who test negative for the disease. Thus, specificity is calculated by taking the true negatives and dividing it by the total number of individuals without the disease, that is true negative plus the false positives. The positive predictive value of a diagnostic test refers to the proportion of individuals who test positive for the disease who actually have the disease, and thus it is calculated by taking the true positives and dividing it by the number of individuals who test positive for the disease, that is true positive plus false positive. The positive predictive value is affected by the disease prevalence, so when the disease prevalence goes up, the positive predictive value also goes up. Similarly, when the disease prevalence goes down, the positive predictive value also goes down. This means that positive predictive value is directly correlated with the pretest probability of the disease. And remember, the pretest probability of the disease is often equal to the disease prevalence. The negative predictive value of a diagnostic test refers to the proportion of individuals who test negative for the disease who actually do not have the disease. And thus, it is calculated by taking the true negatives and dividing it by the number of individuals who test negative for the disease, that is the false negatives plus the true negatives. Just like positive predictive value, the disease prevalence also affects the negative predictive value. In this case, when the disease prevalence goes up, the negative predictive value goes down. Similarly, when the disease prevalence goes down, the negative predictive value goes up. Thus, the negative predictive value is inversely correlated with the pretest probability of the disease, and again, the pretest probability of the disease is often equal to the disease prevalence. The way I keep sensitivity, specificity, positive and negative predictive values straight in my head is by two mnemonics: truths at the top and up. Truths at the top refers to the fact that either the true positive or the true negative is on the numerator for all four of these parameters. Up reminds me which of these truths goes on the numerator and which of the two values I have to add to get the denominator. So the U helps me to remember the formulas for sensitivity and specificity. The first arm of the U tells me how to calculate the sensitivity. We can see that it passes through true positive, so true positive goes on the numerator for sensitivity. It also passes through false negative. That means true positive plus false negative gives me the denominator for sensitivity. The second arm of the U tells me how to calculate specificity. In this case, the arm is passing through the true negative, so true negative is on the numerator for specificity. It is also passing through false positive. That means true negative plus false positive goes on the denominator for specificity. The P helps me to remember the predictive values, so the positive and the negative predictive values. The first arm of the P reminds me how to calculate the positive predictive value. In this case, it's passing through true positive, so true positive is on the numerator for positive predictive value, and it is passing through false positive, so true positive plus false positive goes to the denominator for positive predictive value. Similarly, the second arm of the P is going through true negative, so true negative goes to the numerator for negative predictive value, and it is passing through false negative, so true negative plus false negative goes on the denominator for negative predictive value. This is kind of summarized in my drawing here. For the mnemonic up, remember the U helps you calculate sensitivity and specificity. The first arm of the U helps you calculate sensitivity, while the second arm of the U helps you calculate the specificity. Thus, it is important to remember the order of the arms for sensitivity and specificity. And remember, P is for predictive values. The first arm of the P helps you calculate the positive predictive value, while the second arm of the P helps you calculate the negative predictive value. Let us run through a quick example. Suppose the prevalence of lung cancer in a small town is 10%. Using a new screening test, 90% of the people with lung cancer tested positive, while 50% of the people without lung cancer tested negative. The question asks us to find sensitivity and specificity, positive and negative predictive values. For questions like this in the USMLE, where the prevalence of the disease is given, first we need to construct a 2x2 table. To construct a 2x2 table, assume a population of either 100 or 1000 and then use the disease prevalence to find the total number of individuals with and without the disease. So in this case, if we assume a population of 1000 and 10% of the individuals have the disease, so the number of individuals with lung cancer would be 10% of 1000, which is equal to 100. Conversely, the number of individuals without the disease is 90% of the population, so 90% of 1000 will give us 900. The question prompt also tells us that 90% of the people with lung cancer tested positive. This is basically describing the sensitivity of the test, while 50% of the people without lung cancer tested negative, and that is basically describing the specificity of the test. Since 90% of the individuals with lung cancer tested positive, the number of true positives can be given by taking 90% of the individuals with lung cancer. So 90% of 100, and that is equal to 90. To calculate the false negative, we subtract the number of individuals with lung cancer from the number of true positives. So that is 100 minus 90, and that is equal to 10. We also know that 50% of the people without lung cancer tested negative. That means 50% of the 900 individuals without lung cancer tested negative. So our true negatives would be 50% of 900, and that is equal to 450. To calculate the number of false positives, we take the number of individuals without lung cancer and subtract the true negatives. So in this case, it is 900 minus 450, and that is also equal to 450. This completes our 2x2 table, and we are ready to calculate the positive and the negative predictive values. So far, we've figured out the sensitivity and specificity from the question prompt, and we have completed our 2x2 table. Next, to calculate the positive and the negative predictive values, we can use our mnemonic up. Remember, the first arm of the P tells you how to calculate the positive predictive value, so that will be 90 divided by 90 plus 450, and that is equal to 16.7%. The second arm of the P tells you how to calculate the negative predictive value, so that is 450 divided by 450 plus 10, and that is equal to 97.8%. On your USMLE exams, you may see graphs like this, so let's go over them. This blue, normally represented curve here represents healthy patients, whereas this red, normally represented curve here represents patients with the disease. The y-axis denotes frequency, whereas the x-axis denotes values for a diagnostic test. The dotted line represents a threshold or a cut point for the diagnostic test, where values to the right will represent a positive test result, whereas values to the left will represent a negative test result. The population of individuals who have the disease, i.e. the area under the red curve, who test positive for the disease are noted as true positives, as I'm highlighting with my pen here. Whereas the population of individuals who are healthy and do not have the disease and who also test negative for the disease are denoted as true negatives, as I'm highlighting with my pen here. Conversely, the population of individuals with the disease who test negative for the disease are noted as false negatives that I'm highlighting with my pen here. Lastly, the population of healthy individuals who test positive for the disease are noted as false positives, and that I'm highlighting with my pen here. A question may ask you, what happens to the sensitivity, specificity, the positive and the negative predictive values when the cut point for positive test result is moved from A to B, such that whereas previously this would have been considered a positive test result, now all of this will be considered a positive test result. One of the most important things to remember is that the N's and the P's move together. That means the sensitivity and the negative predictive value move together, and the specificity and the positive predictive value move together. When we move the cut point from A to B, note that all of this extra area under the disease patient curve will now be correctly classified as having the disease. This means that the true positive rate is going up. And note that the true positive rate is basically the sensitivity, so the sensitivity is going up. And since the ends move together, the negative predictive value will also go up. Similarly, whereas previously when the cut point was at A, all of this area under the blue curve was correctly identified as not having the disease, now at B, only this much area under the blue curve will now be correctly identified as not having the disease. And this area under the blue curve will be incorrectly identified as having the disease. Thus, the true negative rate is going down. And remember that the true negative rate is equal to the specificity, thus the specificity is going down. And since the P's move together, the positive predictive value will also go down. Let's run through a quick example. Suppose the disease patients are referring to patients with diabetes mellitus, and the diagnostic test is referring to the A1C measurements. And A refers to an A1C cutoff of 6.5, and B refers to an A1C cutoff of 5. When we move the threshold of diagnosing diabetes from A1C of 6.5 to an A1C of 5, we may catch a lot of patients who have biochemical diabetes but whose A1C is on the borderline, let's say at 6.4, 6.2, 6.1, etc. Thus, the true positive rate will be higher, which means the sensitivity will be higher and the ends move together, so the negative predictive value will also be higher. Conversely, we will also stop classifying healthy patients whose A1C may be on the borderline, such as 5.2, 5.3, 5.4, etc. Thus, the true negative rate will be lower, which means the specificity will be lower. And since the P's move together, the positive predictive value will be lower. Also note that the false positive will be higher in this case because we may be classifying healthy patients who do not have diabetes but have borderline A1C, such as 5.2, 5.3, 5.4. Note that the false negative, which is the area under the red curve here, will be lower in this case because it will be very unlikely that patients with an A1C below 5 will have diabetes. Let us look at an example of the other scenario. Assume again that we are talking about diabetic patients and we're talking about A1C as a diagnostic test. This time we move the cut point from 6.5, which is C, to 8, which is equal to D. In this case, what happens to the sensitivity, specificity, positive and negative predictive values? Note that when the cut point is at D, the number of healthy patients who may have borderline A1C, such as 6.6, 6.7, but who do not have diabetes, increases. That is, the true negative rate increases. Since the true negative rate is equal to the specificity increases, and since the P's move together, the positive predictive value also increases. Also note that our ability to detect diabetic patients who may have slightly increased A1C at 6.7, 7, 7.2, 7.5, or 7.7, etc. will be lower. This means that our true positive rate will be lower. Whereas previously we could have detected all of these patients. Now we can only detect these patients with a new cut point at D. Since our true positive rate is lower, our sensitivity is also lower in this case. And since the ends move together, our negative predictive value is also lower in this case. To maximize both the sensitivity and the specificity of a diagnostic test, the ideal cut point is given by the intersection of the two graphs. So that would be here. Now let's shift gears a little bit and talk about ROC curves. The receiver-operator characteristic curve, or an ROC curve, is a graphical representation of the true positive rate. And remember, the true positive rate refers to the sensitivity, which is represented in the y-axis, and the false positive rate, which is given by 1 minus the specificity, and that is given on the x-axis, of the diagnostic tests for various cutoff points or threshold values. The goal of an ROC curve is to maximize both the sensitivity and the specificity. In an ROC curve, so we have sensitivity on the y-axis and 1 minus the specificity on the x-axis. And remember, the maximum value for both the sensitivity and the specificity would be 1.0. Thus, the closer the value is to 1 on the y-axis, the higher the sensitivity, and the closer the value is to the 0 on the x-axis, the higher the specificity, since the x-axis represents 1 minus the specificity. The area under the curve represents diagnostic accuracy, where the larger the area under the curve, the larger the diagnostic accuracy. The best theoretical test will have an area of 1, and it would look like something like this, like a square. A useless test will follow the diagonal line with an area of 0.5. So a useless test will look like this. A useless test is also called a random classifier because it is similar to tossing a coin. This is useless because guessing will produce similar results as administering the test. In this slide, we can see several ROC curves where each of these lines represent a diagnostic test. Note that the red dashed line is a random classifier or the useless test. The blue point here shows the ideal cutoff point for a diagnostic test, where the true positive rate or the sensitivity is equal to 1 and the false positive rate or 1 minus the specificity is equal to 0, which would produce a specificity equal to 1. And remember, the ideal ROC curve will look like this. The closer an ROC curve to the ideal curve, the better the diagnostic test. So in this case, the blue line represents the best test because it is the closest to the ideal ROC curve. The closer the ROC curve to the diagonal line or the random classifier, the worse the test is. So in this case, the green line represents the worst test because it is closest to the random classifier. The blue arrow here represents the ideal cutoff in the best test. This is usually the leftmost corner or the inflection point, because this is the point where we are maximizing both the sensitivity and specificity. Moving on to the section on properties of a screening test. First, let's talk about precision or reliability. The precision or the reliability refers to the reproducibility of a test, that is, how closely repeated measurements match each other. Thus, a test with high precision will have minimal random error, and this is very important to know. This also means that a test with high precision will have a smaller standard deviation. On the other hand, the accuracy or validity refers to the trueness of the test results, that is, how closely the test results match the reality. Thus, a test with high validity will have minimal systematic or non-random error or bias, and this is very important to know. Oftentimes, precision and accuracy are explained in graphs like this. Let's say the true value lies in the middle of the crosshairs here. If the test measurements sort of approximate the true value, they can be deemed accurate. And if the test measurements lie close to each other, they can be deemed as precise. So in the first plot here, the test measures sort of approximate the true value in the middle, but they are not close to each other, so the test result is accurate but not precise. In the graph here, the test results are both close to each other and approximate the true value, and thus the results are both precise and accurate. In this case, the test results are close to each other, but they are not approximating the true value, thus they are precise but not accurate. And in the last case, the test results are all over the place and they are not approximating the true value, and thus they are neither accurate nor precise. A screening test is the initial test that is done on patients where the negative result rules out the disease. That is, the test has a low false negative. Very, very high yield to know that an ideal screening test will have high sensitivity, which leads to low specificity and high false positives. Remember that false negatives are patients with the disease who test negative, so that is this portion of the curve here. We can see which is very, very small for an ideal screening test. High sensitivity means that the test has a high true positive rate, which are the patients with the disease who test positive for the disease. If the screening test threshold is here, that means anything to the right of this side are testing positive. So all of this area represents a true positive rate, which for a screening test should be high. Conversely, the false positive rate is given by the healthy patients who falsely test positive for the test results. If the screening test threshold is here, all of these healthy patients will be testing positive. This means that the screening test has a high false positive rate. And remember that false positive rate is 1 minus the specificity, so the specificity is also low. And remember, the specificity is given by the true negative rate, and we can see that the true negative rate is given here, which is lower than what it could be had the screening threshold was here. A confirmatory test confirms the presence of the disease and is usually done after a screening test. Importantly, confirmatory tests have low false positive rates. Very, very high yield to know that an ideal confirmatory test should have a high specificity, which leads to low sensitivity and high false negative rates. So in this case, if the threshold for the confirmatory test is here, where everyone to the right of this threshold is considered positive for the test, we can see that the false positive rate, that is the number of healthy patients who test positive, would be low, which is the area here. The true negative rate, that is the number of healthy patients who correctly test negative, is the large area here, which basically signifies a high specificity or a high true negative rate. Conversely, the false negative rate, that is the number of diseased patients who falsely test negative, is high here, which also means that the true positive rate or the sensitivity is lower than what it could be had the threshold been here. A very, very high yield mnemonic to know for your board exams is the snout and spin. Snout refers to screening tests which should have high sensitivity. That means that a negative test result rules out the disease. Spin refers to confirmatory tests which should have high specificity, where the positive test result rules in the disease. Also very, very high yield to know is that sensitivity and specificity does not depend on the disease prevalence. Also note that there is trade-off between the sensitivity and specificity for a diagnostic test, as we have seen previously when we moved the thresholds or the cut points. Two important biases to keep in mind for diagnostic tests are the lead time bias and the length time bias. In this case, the lead time is the time between the detection by the screening test and its usual clinical presentation and diagnosis, such as the disease's symptoms or traditional diagnostic criteria. Very important to know is that there is no apparent effect on the prognosis or mortality rates in this bias, and this is primarily seen in terminal diseases with lower cure potential, such as adult cancers. Two possible solutions for lead time bias include number one, adjusting for the severity of disease when detected by screening. For example, with adult cancers, noting the stage of the cancer at the time of detection by screening. A second possible solution is using mortality rates instead of the survival time. Here is an example of lead time bias that can be seen with cancer screening. Suppose we have two scenarios where the onset of cancer happens at the same time point and the death from the cancer happens at the same time point. Suppose in the first scenario, we use a screening test to detect the cancer, so the cancer is detected earlier at this time point. Whereas in the second scenario, the cancer is naturally detected from its symptoms at this time point. Note that because the mortality happens at the same time point since the onset of the symptoms, detecting the cancer earlier did not lead to an improvement in the mortality rate or improvement in the prognosis of the cancer. The difference in the time point between the detection of the cancer by the screening and the detection of cancer through its symptoms is known as the lead time, as shown here. Again, lead time bias is happening because the death is occurring at the same time regardless of the early detection of the disease by screening. The length time bias is a form of selection bias where the screening test preferentially detects less aggressive and slowly progressive forms of the disease. Thus, the more aggressive forms of the disease either die off and/or are not detected. This apparently leads to an increase in the survival times due to the screening. A solution to this, like lead time bias, is to adjust for the severity of the disease when detected by screening. For example, with adult cancer, noting the stage of the disease at the time of detection by screening. Here is the example of length time bias seen with cancer screening. Suppose we have 12 patients who suffer from a type of cancer. The vertical line represents the onset of their disease. The horizontal line represents their survival time with the disease. The longer the horizontal line, the more the patient survived with the cancer, which may represent a less aggressive form of the cancer. Whereas the shorter the horizontal line, the less time the patient survived with the cancer, which may represent a more aggressive form of the cancer. The arrow at the end represents patients who have survived the cancer, whereas a cross at the end represents patients who have died from the cancer. The blue lines represent the cases that were picked up by the screening, and the black lines represent cases that were not found by the screening test. If the dotted line represents the time when the screening was done, we can see that among the 5 patients picked up by the screening test, almost all of them have very long survival times, and almost all of them have survived at the end. So we have 4 patients who survived and only 1 who passed away among the patients who were discovered by screening, which brings the percentage of patients who survived the cancer at 80%. Now, if we look at all 12 patients who suffered from the cancer, we can see that only 5 survived the cancer at the end, which brings the total percentage of patients who survived from the cancer at only 41.7%. Thus, because the screening is detecting a less aggressive form of the cancer, we can see that the screening appears to lead to a better survival. In our last section of this module, we will discuss probability. The pretest probability is the probability a patient has a specific disease. Very, very important to know is that the pretest probability is equal to the prevalence of the disease and therefore affects the positive and the negative predictive values and does not affect sensitivity, specificity, and we will learn later the likelihood ratio. The pretest probability is directly proportional to the positive predictive value and inversely proportional to the negative predictive value. Thus, if the pretest probability goes up, the positive predictive value goes up and the negative predictive value goes down. Conversely, when the pretest probability goes down, the positive predictive value goes down and the negative predictive value goes up. The post-test probability, as the name suggests, is a probability that a patient has a disease after diagnostic testing. The post-test probability is calculated by taking the pre-test probability or the prevalence and multiplying it by the likelihood ratio. We will discuss the likelihood ratio in the next slide. The likelihood ratio assesses the value of performing a diagnostic test. It asks the question how likely that an individual has a disease after diagnostic testing. That is, it helps us to calculate the post-test probability. Very, very important to know is that the likelihood ratio is used to make inferences on single or individual patients. Likelihood ratio does not depend on the prevalence or the pretest probability. This is because the likelihood ratio is calculated from sensitivity and specificity, which we know do not depend on the prevalence or the pretest probability. The range from likelihood ratio goes from 0 to positive infinity. Thus, when the likelihood ratio is less than 1, this means that there is decrease in the probability of presence of the disease. When the likelihood ratio is equal to 1, this means that the pretest and the post-test probabilities are similar. That is, there is no beneficial effect in doing the test. When the likelihood ratio is greater than 1, this means that there is an increase in the probability of the presence of the disease. A positive likelihood ratio refers to the probability that an individual with the disease tests positive compared to an individual without the disease testing positive. A positive likelihood ratio is calculated by taking the sensitivity and dividing it by 1 minus the specificity. A positive likelihood ratio greater than 10 indicates a large increase in the probability of the disease, that is, a high test specificity. This makes sense as a high test specificity would be closer to 1, which would make the denominator of this fraction small, which would make the overall fraction a very large number. A negative likelihood ratio refers to the probability that an individual with the disease tests negative compared to an individual without the disease testing negative. A negative likelihood ratio is calculated by taking 1 minus sensitivity and dividing it by the specificity. A negative likelihood ratio of less than 0.1 indicates a large decrease in the probability of the disease, that is, a very high test sensitivity. This makes sense as a high test sensitivity would be closer to 1, which would make the numerator of this fraction small, which would make the overall fraction small as well. Here are a few examples of how likelihood ratios affect the post-test probability of a disease. Note that when likelihood ratio is equal to 1, the post-test probability of the disease does not change, and thus there is no effect of doing the testing itself. When the positive likelihood ratio is about equal to 10, there is a 45% increase in the probability of the disease. Conversely, when the negative likelihood ratio is equal to 0.1, this indicates a 45% decrease in the probability of the disease. Let's run through a quick example for likelihood ratio. Suppose we have a study investigating various diagnostic markers for glioblastoma, and this resulted in the table to the right. So here we have 3 biomarkers A, B, and C, and their respective sensitivity, specificity, positive and negative likelihood ratios. The first question asks us, a patient is most likely to be free from glioblastoma when which of the biomarkers is negative? Remember, for individual patient-level decisions, we need to look at the likelihood ratios. Here, we're talking about a negative test result, so we should be looking at the negative likelihood ratio. And for this specific case, we're looking for the biomarker with the lowest negative likelihood ratio, which is biomarker A. Note that the sensitivity and the specificity of the biomarkers can also serve as useful hints. For this question, we're basically asking which biomarker is the best screening test for glioblastoma. Thus, we're looking for the biomarker with the highest sensitivity, and that also happens to be biomarker A. This is not surprising, as we discussed in the previous slide, that the lower the negative likelihood ratio for a test, the higher the sensitivity for the test. The second question asks us, a patient is most likely to have glioblastoma when which of the biomarker is positive? Again, for individual patient-level decision, we're looking at the likelihood ratios. Since we're talking about a positive test result, we're looking at the positive likelihood ratio. For this specific question, we're looking at the biomarker with the highest positive likelihood ratio, which is biomarker B. Also note that, just like the previous question, the sensitivity and the specificity can serve as useful hints. In this case, we're looking for the biomarker that can serve as a confirmatory exam for glioblastoma with the highest specificity, which also happens to be biomarker B. Again, this is not surprising, as tests with higher positive likelihood ratio are more likely to have higher specificity. Continuing the example from the previous slide, the third question asks us, assuming a patient has glioblastoma, how likely are they to test positive for biomarker C compared to a patient without glioblastoma testing positive for biomarker C? So this question is basically asking us what is the positive likelihood ratio for biomarker C. From the table, we know that the positive likelihood ratio for biomarker C is equal to 2.5. The last question asks us, assuming a patient has glioblastoma, how likely are they to test negative for biomarker B compared to a patient without glioblastoma testing negative for biomarker B? So this question is asking us for the negative likelihood ratio for biomarker B, which from the table we know is 0.32. Shifting gears a little bit, let's talk about properties of probabilities. Independent events are probabilities of events that are not contingent upon one another. As an example, if you're asking what is the probability for a patient to have a girl with an autosomal dominant disease, in this case, the probability of having a girl is independent from the probability of having a child with autosomal dominant disease. The multiplication rule denotes that for independent events, the combined probability is calculated by multiplying the individual probabilities. Similar to the previous example, if we are asking what is the probability of having a boy with autosomal dominant disease, we know that the probability of having a boy is independent from the probability of having a child with an autosomal dominant disease. So in this case, we'll simply multiply the two probabilities. That is the probability of having a boy multiplied by the probability of having a child with an autosomal dominant disease. The addition rule states that if we have two events, event 1 or event 2, the probability of event 1 or event 2 occurring will be equal to the probability of event 1 plus the probability of event 2 minus the probability of event 1 and event 2 combined. For mutually exclusive events, which means that event 1 and event 2 never occurs together, such as the presence or absence of neurofibromatosis 1 in a child, the probability of event 1 and event 2 occurring together will basically be equal to 0, and thus the probability of event 1 or event 2 will be simply equal to the addition of the probability of two events, that is the probability of event 1 plus the probability of event 2. Conditional probabilities are denoted like this, where probability of event 1 given event 2, and we are basically asking what is the probability of event 1 occurring given that event 2 has already occurred. A few prominent examples of conditional probabilities that we have already discussed include the sensitivity, where we're asking what is the probability that the patient tests positive for the disease given that they already have the disease. Conversely, with positive predictive value, we are asking what is the probability that the patient have the disease given that they have tested positive for the disease. Bayes' theorem provides us with a tool to calculate conditional probabilities. Thus, the probability of event 1 given event 2 will be equal to the probability of event 2 given event 1 multiplied by the probability of event 1, and all of this divided by the probability of event 2. The law of total probability denotes that if we have probability of something, such as probability of A, that is equal to probability of A given V multiplied by the probability of B plus the probability of A given not B multiplied by the probability of not B. Now, you do not have to memorize these formulas. They're given here so that I can illustrate an example in the next slide. Here is an example that we have previously encountered on the section in sensitivity, specificity, positive and negative predictive values. Suppose the prevalence of lung cancer in a small town is 10%. Using a new screening test, 90% of the people with lung cancer tested positive, while 50% of the people without lung cancer tested negative. The question asks us to find the sensitivity, the specificity, and the positive predictive value. Recall that the sensitivity and specificity are already given on the question prompt. The prevalence of the disease, which is equal to the probability of D positive, is equal to 0.1 or 10% from the question prompt. This means that the probability of being disease negative is equal to 1 minus the probability of being disease positive. So 1 minus 0.1, and that is equal to 0.9. The sensitivity is equal to the probability of being test positive given disease positive, and that is equal to 0.9 from the question prompt. And the specificity is equal to the probability of being test negative given disease negative, and that is equal to 0.5 per the question prompt. This means that the probability of being test positive given disease negative is equal to 1 minus the specificity, so that is 1 minus 0.5, which is equal to 0.5. The positive predictive value is equal to the probability of being disease positive given test positive. Using Bayes' theorem, that will be equal to the probability of being test positive given disease positive multiplied by the probability of being disease positive and divided by the probability of being test positive. Using the law of total probability, we can expand out the probability of being test positive as the probability of test positive given disease positive multiplied by the probability of disease positive plus the probability of test positive given disease negative multiplied by the probability of being disease negative. So now we can plug in all of our numbers. The probability of test positive given disease positive is equal to the sensitivity, so that is 0.9. And the probability of disease positive is the prevalence, so that is 0.1. The probability of test positive given disease positive is the sensitivity, so that is 0.9. The probability of disease positive is the prevalence, so that is 0.1. The probability of test positive given disease negative was previously calculated here, so that is 0.5. And the probability of disease negative was 1 minus the prevalence, so that is 0.9. Completing out this equation, we get 0.167 or 16.7%, which is exactly what we got when we used our 2x2 table method. Note that this approach is too complicated for a USMLE exam. I strongly recommend constructing your own 2x2 table by assuming a sample size of 100 or 1000 and then using the up mnemonic to calculate this positive predictive value and the negative predictive value. In the last slide of this module, let's briefly discuss decision trees. A decision tree is a visual representation of all of the outcomes, sometimes presented along with their probabilities. A classic example for a decision tree is the pedigree as shown here. A pedigree basically shows how a disease is transmitted within a family tree. Sometimes we can also find the probabilities of disease transmission across each of the branches. You have reached the end of this module. Thank you so much for bearing with me. Stay well and see you in the next module.